It's my very great pleasure to welcome Laura Dietz to be our colloquium speaker today. Laura got her PhD at the Max Planck Institute and did a postdoc at UMass with Andrew McCallum and Bruce Croft before becoming an assistant professor at the University of New Hampshire. Laura's work sits at the intersection, well, you can see from her title here, it sits at the intersection of text understanding, text retrieval, search, and the use of knowledge bases and knowledge graphs. And within that area, Laura has a rather diverse portfolio. She has looked at things such as retrieving entities from the knowledge graph, for example, which entities are appropriate for this query or this document. She's looked at how you represent the different aspects of entities, how you use entities to and other information about them to improve search. So I like her work because it dovetails with my own, so that's great. But also, it's much of the work that we do in text understanding today is based on just the text alone, and Laura's bringing in other structured resources that we might have available, perhaps very reliable or perhaps a little noisy, in order to improve the understanding of the text. So she does great work in that area. She's also an organizer of things. She's very active. She's been one of the organizers of the KG for IR workshop series, which brings together people in this area. And I think for 3 years, she created and organized the TREC complex answer retrieval track. So in addition to her own work, she helps create forums and problems that drive the research of the research community. So I think it's great to have her here today, and I think the work that she's going to talk about is probably rather different than a lot of the other work we'll hear this semester. So with that, thank you, Laura, for taking the time to do this with us today, and I look forward to hearing your talk.
Thank you so much for the introduction. Yeah, I usually I like XKCD a lot, and I hope I'm not alone in this room. And I like XKCD because it often really resonates with me and with sort of like some of the frustrations that I have with software today and maybe the world today, where I often think we can do things a lot better. Before I got my PhD, I was actually in software development, was more like a product owner. And I still sort of like have this angle of looking at what we have and thinking, well, we should be able to do better here. One of the XKCDs I selected for this talk is the one up here in the corner. It says, sort of like, group of people talking to one another. One says, I'll be honest, we physicists talk a big game about the theory of everything. But the truth is, we don't really understand why ice skates work, how sand flows, or where the static charge comes from when you rub your hair with a balloon. And these are sort of like things I'm already super in love with this, right? Like I have exactly these kind of questions. I'm very interested in sort of popular science and kind of like understanding different bits and pieces about the world. And often I kind of like stumble upon something, and it's often a topic I don't know anything about. I don't know how ice skates work. I have like an unhealthy layperson's knowledge about something with like ice melting and then it being like slippery so we can go forward, but then why wouldn't we go sideways? So I don't know, but I want to know. And finding information about topics you know very little about is kind of like often a really frustrating process. And this is kind of one of the things where sort of like my big 10-year vision is going towards. I'm always saying that one of my big visions is to create Wikipedia-ish articles for topics that don't yet have a Wikipedia article. And I think that's sort of like ultimately a different way of doing information retrieval and getting like access to like information in a way that we don't have access at the moment, which is different from Alexa, although maybe Alexa could learn something from it. It's different from web search, although maybe web search can sort of like also learn from it. And it's sort of like a different way of trying to find out stuff and make it a little bit easier for users beyond the old goodies of like click logs and sort of like learning a lot of one particular user. I think there should be sort of like an expression of something we want to know, like how ice skates work, and there should be sort of like one best answers without knowing a lot about what I know or don't know. There should be sort of like something better than what we currently have. All right, so this talk, I'm going to talk about a whole bunch of different things. I picked one work to focus a little bit more on, which is called ENT Rank. on the whole, it's about sort of finding relevant entities through text and knowledge graphs, but then use them to bring us back to text and kind of like help us draw the different connections. Because we will probably forget to acknowledge NSF, but NSF makes me acknowledge things. Some of this work that I present today was supported by the National Science Foundation. Can we skip? Here we go. All right. So we already talked about sort of like the need for open-ended information needs, such as, you know, how ISKs work, why is the UK leaving Europe, why is cash flow important for investment, honestly a topic I know very little about, effects of water pollution, or things like, you know, we had this diesel scandal with Volkswagen a couple of years ago. How did that affect other automakers in Germany like Daimler? Okay, and in each of these queries, maybe some of them can maybe be interpreted as yes/no questions, but when I'm asking these questions, I'm not interested in the yes/no answer. I'm interested in like, if yes, why? If not, why not? What are the causes? What are the involvements? What's the controversy? What's the backstory? Or in short, what do I need to know to actually understand whatever answer that is to something I would like to know? And often, so Jamie mentioned that I was organizing the TREC complex answer retrieval track. Remember, there were answers, but there are no questions, because often the questions are like very latent, like topic question mark. That's, I think, a very good question that's like really open-ended. And the open-endedness is, I think, what I think is difficult and also interesting. All right. So the bigger idea here behind generating Wikipedia articles for topics that don't have one is that we want to train computers to recycle web content that can write comprehensive articles in response to a search query. Okay, so there's a lot of NLP, natural language generation, information retrieval, and like reasoning all baked together in this like one vision. And the main issue is like, well, you know, if we have a Wikipedia article on the topic, that's great. And often people look for information, that's where they turn to first. But like the information is sometimes, you know, limited. Wikipedia seems like it covers everything, but there are actually a lot of areas that are not well covered in Wikipedia, or they're just like horribly out of date. If it's not on Wikipedia, most people turn to web search, but then we have to manually sift through many web pages, which is really no fun. I mean, if you think this is a lot of fun, please come talk to me. I might actually pay you to do some of this for me. But I just assume that most users also don't think that's very much fun. Instead, we just want to have something coherent that we can read. And after we are done reading it, we have learned something. Before I dive further into the talk, I want to first clarify what I mean by entity. When I say entity, I mean something like a person, place, gene, protein, event, thing, or anything else that has an entry in a knowledge base. And when I say knowledge base, I mean Wikipedia, let's be honest. But like many of these things could also be replaced with other knowledge bases. Maybe not NCBI knowledge bases, but like knowledge bases that have a lot of like text content associated with them. And this is sort of like my cartoon notation of an entity. Like even if it's, you know, a car, I would still be represented by a stick figure. Stick figure is my cartoon notation for entity. And each entity has a couple of names, like these name tag things. There might be relations to other entities or types and categories. And that's like something that's often undervalued. I also have a longer article about this entity, namely whatever Wikipedia has to say about it. So I have these sort of like semi-structured representation of an entity, which I can sort of like stick into a search index. Either I can just create a search index over Wikipedia pages, and I can sort of like call that a knowledge base index, because whatever query I have, I can just issue against this Wikipedia index and a retrieval page, and every page represents one entity. That was like my definition here. So by retrieving from Wikipedia, I automatically do something like entity retrieval. But if I have more structured metadata-oriented entities, I can also create a search index for that. And that's sort of like kind of like the very basics of what I would call entity retrieval. I will talk a lot more about this during this talk. Right, so in TREC complex answer retrieval, the vision was the user gives me a query. And this query mentally is intended to be sort of like the title of an article that then we are trying to generate, right? Sort of like Zika, for example, Zika fever. Tell me everything about Zika fever, and that will be the query. And as a response, what I want the computer to generate is sort of like text that we have predominant facts and introduction first, and then we have sort of like different details about different subtopics next. And at the same time, we also have sort of like maybe a little knowledge graph that sort of like goes along with this query. So the idea is that we have both something that's designed to be consumed by humans, namely this text, and something that can be further consumed by computers, namely a mini knowledge graph on the topic of the query. All right, so that's sort of like where I'm heading to. So how do we get there? So, and that's just like the most simplest way to think about my work is when we have the query, first thing we do, we try to find out what is even important to mention if you want to compose an article of the query, like which entities are relevant. Then we kind of like might think about how are these entities related and which of these relations are also relevant for this query. And you might often have like two entities that are related, but while these two entities are relevant, this relation is not really important. That's kind of like a common problem, and that's actually something I've been fighting with. So once we have that, we can now go and like look at the text and kind of try to find where are some of these entities and relations that we identified as relevant are actually expressed. And then we can try to do some clustering and try to slowly build up this article from the bottom up. Right? This is sort of like a very different approach than GPT-3, which says like, you give me the query, that's a prompt, and I just go and generate the rest. And I think so that this is like a little bit more focusing first on identifying what the content is, and then having the nice grammatical language sorted out later. Okay. And by the way, if you have any questions at any time, please do interrupt me. I can always skip over things later, but there's like very little point for me just talking if you guys are like lost or have like questions. Okay. All right, so I want to quickly talk about some early work of mine, which is now, wow, this is kind of like maybe like 6-7 years ago. And it was sort of like work where I think we were at the right time, where the Freebase knowledge graph was already released, and someone released, I think Google released entity link annotations of like a large search index. So we had now finally a big corpus with entity link annotation. And I think Jamie and I'm not sure that you guys remember Chen Yan Chong. So they were kind of like, they were next in line, and we would do a strong conference before them. So I don't want to say that this is just my idea. I think a lot of us it's sort of like similar ideas, but I want to very quickly talk about them to kind of like to set the stage for what comes next. So the idea is we want to first find sort of relevant entities. Let's say here's a query. Let's say how did the diesel scandal affect Daimler? And we're trying to find entities that sort of like are important to be mentioned in an answer that would be sort of like justified with this for this query. Like this would be Daimler, it would be Volkswagen, which was the company that had the big diesel scandal, the diesel scandal itself, and maybe emissions tests, and there are a couple of like other things that we should mention on an article on this topic. All right. So how do we find these entities? Well, first idea, and a lot of people have tried that, is we just take the query and we run an entity linker on that query. By the way, if you don't know what an entity linker is, my 30-second explanation would be it's a piece of machine learning that, given a string or given a sentence, would spot entities and would line these mentions to entries on Wikipedia or whatever knowledge base you have. So if you have that, it's really nice. We can just like give it, for example, queries, and the entity linker would identify, oh, Daimler, that's an entity, and in particular, that's this entity. That's certainly like one source of information. The only problem is things like Volkswagen and emissions testing will not be found this way because they are not mentioned in the query. And that's very common. This is sort of like where information retrieval is very different from semantic matching, because in one case, it's sort of like symmetric, right? We ask like, does this sentence entail this other sentence? Is this kind of like mostly equivalent? Where in queries, often we have a prompt, and the reason why this query is being asked is because the user wants to know stuff. And obviously that should be contained in that document that we provide this. So it's sort of like this asymmetry that makes things very challenging. So the next approach to like find these entities, and that's also done by various different people, I don't want to claim that I was the one inventing this, is just create like a search index of our knowledge base, as I said before. Now we can take this query, we can run it against the search index, and we find more entities. In particular, we find entities that mention these keywords on, for example, the Wikipedia page or in the description field. Okay. The third thing is information retrieval. People call that relevant feedback or pseudo-relevant feedback. If you don't know what that means, here's my 30-second explanation. We have a query. We have a search index over documents. Now we can retrieve these documents and we pretend that these documents are actually relevant for this query. Now we can run an entity linker on these documents, and we can pretend that every entity that's mentioned in here is probably also relevant if it's contained in a document that was relevant. So that's sort of like a dangerous game, which is actually, it's a really strong baseline, but it also sometimes just goes horribly wrong. But it's definitely something to kind of like include and kind of like then, you know, consider as whether these entities are relevant. And so at the end, we can like use all three sources and we combine them to identify which entities are actually relevant. Once we have a set of relevant entities, we have like some guess of which could be relevant, we can use other documents and we can just like match entities, query terms, terms in the article of that entity, other related entities. If all of these things are like mentioned in here, we can sort of take that as like multiple different indicators, and we can use that for a better document ranking, and that actually kind of works really well, right? So kind of like ignoring entities is like a huge mistake if you're an entity, if you're an information retrieval. They're like so helpful, and in particular, they are also like things where, especially once you have an entity linker, you can't like eradicate like common problems with language like synonyms and polysems, because the entity linker essentially like avoids all these like linguistic problems for us. So that's kind of like, that was really nice. So we kind of did some analysis which of these three indicators or like sources of information is actually most useful. The first one is really high precision, but you're missing a lot of entities, in particular entities that then would be in relevant documents, even if the query terms are not really mentioned. This here is kind of like a good idea, and I think most of semantic web is kind of like focusing on number two. But number two, it's still kind of surprisingly not working really well. The strongest feature by far is actually using pseudo-relevant feedback. And the reason is that often there are entities that are relevant, but the Wikipedia article is out of date. So they might not mention that they are connected to this query. But if you have a recent news corpus, you might actually identify where these query terms are being discussed in the context of these other entities. And that's sort of like a surefire way of finding these entities. And I want you to remember this because this is something I will come back to towards the end of the talk. All right. So we did this thing with entities, and then I had a lot of people, lots of friends that worked on relation extraction. So I was like, oh, let's do something with relation extraction and see whether that actually also helps us here. That kind of like led to like two pieces of work, which are still sort of like hanging there because the results are not in the sense that I'm really happy with. They kind of pointed more to like big problems. Okay, so let me tell you a little bit about problems. Maybe you have a solution, please let me know. Okay. Like if you want to identify relevant relations in a knowledge graph, that means we have like some of these entities that we identified in the previous step that we think are relevant, and we have these other entities in between that are connected like through various kinds of relations. Some of these relations are relevant, like these ones here, and then there are other relations that are just not really relevant. They're correct. It's not a matter of like whether these relations exist or not, but it's just about whether these relations actually matter in the context that we're looking at. And there's sort of like many naive approaches of using PageRank or using, by the way, PageRank will not work, especially if you have a dense knowledge graph, or looking at sort of like entities that are sort of like on shortest path between these two entities, and they all kind of work-ish, but then also often like make a lot of like stupid mistakes. So that's maybe a little bit too simplistic to think about it. In particular, if you have an entity that's relevant, often it's connected to many other entities directly, which are not relevant. So it's just like, even like distance in the graph is not necessarily meaningful. There were a lot of papers in like 2013-ish that used PageRank on a knowledge graph, where they first find some seed entities and then like walked around, and they're like, yeah, it works, it works. And if you go, if it's every year, the results were kind of like less impressive. And they were less impressive because the knowledge graph has grown in coverage. And don't get me wrong, coverage is a great thing. But you know, in 2013, you have a really sparse knowledge graph that only contains the most important information. So whatever information you find is probably going to be important, because only the most important things are going to be there. But if you add more coverage and you add more like other topics as well, the graph kind of like looks like this one here on the right hand side, but actually more like this, or well, it's still kind of like an understatement. It's actually like that, right? Today knowledge graphs look like a huge mess because they have a lot of coverage, and coverage is good, but we have to like deal with the mess, and just using PageRank is not going to cut through it anymore. Okay. And in particular here, you have these like huge hub nodes like New York City, California, United States. They are like actually relevant entities in some context. And if they are relevant, like they are connected to so many other entities. Like I think New York City has, I think between like a couple of 100,000 to like 1 million of inlinks. So if you would think, oh, we just used the direct neighbors, you have now added 1 million other entities to your set of relevant entities, and that is between, you know, a hot dog stand and like a train station, and you know, well, it's 9/11 today, right? So ground zero, right? And depending on what you're looking for, some of these are relevant, some of these are not. So kind of like this direct neighborhood is just not enough of a signal for it to actually work with this kind of graph, which is sad because I really like graphs. So I'm still kind of like hunting after all these years, actually trying to find a way of like sorting through this graph and identifying which connections are actually relevant versus not. Because I had so many friends that worked on relation extraction, and they were all starting their papers with relation extraction. We work on relation extraction because it's good for information retrieval. And I said, well, why is it good for information retrieval, you think? And they say, oh, well, we have a query, we retrieve relevant documents, we run relation extraction, therefore we have relevant relations. And that's sort of like, I was like, let's have a closer look at that and put maybe a question mark here at the end, like put it as a research question. If you don't know what relation extraction means, here's my 10-second explanation. We have a document with a sentence in it. In the sentence, we can mark entities and already have them like linked with our entity linker. And the relation extractor would tell us whether this sentence expresses whether this and this entity are in a particular relation, such as maybe the entity with the hat works for the bald entity. We can sort of like just use this and actually try this out, because we do have information retrieval benchmarks, and all we need to know is like which relations are relevant. And we did this both for supervised relation extraction with schemas and unsupervised relation extraction with OpenIE, and we kind of like found in both cases like similar results. This is kind of like just like one example where we identify that if we use a relation extractor on this, we find a lot of relations are actually relevant. However, half of the relations that we find are not relevant, like down here, these are like the dashed ones. What's interesting, and actually it's really exciting, we find a lot of relations that are relevant and were not contained in our knowledge graph. You might remember like a second ago I complained that our knowledge graph has too many edges, most of which are not relevant. Now I'm telling you that we found relevant stuff that wasn't even in our knowledge graph. Okay, so the real world is even bigger than we thought. And the real problem is like actually even harder. But it's sort of like, it's like just using sort of like this simple question mark here, I would say, no, it wouldn't automatically lead to relevant relations. There's like more work that's kind of like needed. Right, so I could talk more about this, but I'm going to skip it, but you can ask me later about it. So there's another problem with relation extraction that is often like triple or like quadruple or quintuple based. And like interesting relations are often a little bit more complicated. Like here we have some about like Volkswagen had intentionally programmed turbocharged direct injection diesel engines to activate some emission controls only during laboratory emissions testing. So if you have that text fragment and you try to write an extractor of how Volkswagen is related to the diesel scandal, it might be hard to just get this out of just this piece of like text fragment. And I think many of these relations are kind of like just extend beyond one sentence. They include multiple intermediate entities. And on the whole, the problem is a little bit more complex, excuse me, than just relation triples plus co-reference. Especially when they span over like longer context and we're trying to extract really abstract relations for which we don't have a lot of like training data. So but I know that there are like lots of people working on it, and I'm like excited to like try some of their methods, some of their results soon. So if you're working on that, please do let me know. Make sure I know your work. Like here's another real-world example about pollution and eutrophication. So here the problem is, if you bring a lot of fertilizers out on the field, and right next to the field you have a river, with the next rainstorm, the nutrients that you put on the field land in the river and get washed down, and then you have sort of like these dead zones where you have a lot of algae growing. Algae, like fertilizer, they grow a lot and they suck away all the oxygen from the water. So everybody else who lives in the water and needs oxygen is going to die, and then decomposes, and you have even more nutrients in the water. So it's like a really sad feedback loop that we have here. And it's sort of like, it's just an idea of like, well, we have these pieces of text, all that information is in here, but it's just not so easy to extract it with the methods that we currently have. All right, so that's kind of like, so I was talking a lot about problems here and maybe how we have maybe solutions for the problem in the future. Let me talk a little bit about some work that I published last year at CGIA about entity ranking that kind of like tries to make use of some of the text indicators, and it's really more like a rather generalized framework that we're still sort of like working on and exploiting on, and some of this relation extraction work should go in there and will go in there. All right, so the task here is, and by the way, I don't know the time, so let me know if I'm kind of like slowly running out of time so I can wrap up. So the task I'm working on is entity ranking, but that's just an example task. The framework is a little bit more general, that you can do like any kind of ranking with the help of other things. But before I make it like too abstract, let me just talk about the task of entity ranking with documents. So in entity ranking, we're given a query such as Zika fever. Okay, some of you might still remember. And the goal is to retrieve entities from a knowledge graph that are relevant, such as, you know, in the case of Zika, the Aedes mosquito, the Guillain-Barré syndrome, and the flavivirus, because Zika fever is triggered by a flavivirus. Okay, and again, when I said knowledge graph, I actually mean Wikipedia. Most of the time, when people talk about entity ranking, they're motivated like this. They say many users on the web are looking for entities, and they usually have a citation from Jeffrey Towns. And that's true, right? I mean, people ask who won the women's soccer championship, to which the answer will be United States of America. And that's all nice and well. It's not exactly our motivation here, but this approach still works well even on this kind of entity ranking. Okay, but what we were really after is, you know, what I said with TREC complex answer retrieval. So we give them a query such as, tell me everything about Zika fever. And then we want to retrieve entities that either must, should, or can be mentioned on a comprehensive article about this query. And if you take the Wikipedia article from Zika fever, you can look which entities were mentioned on that article. So you can sort of construct yourself like a ground truth, which is really nice. But it's sort of like it's a different texture of an entity retrieval problem than this kind of question answering driven entity retrieval. But still kind of like similar things apply to both. Remember how a couple of slides back I mentioned to you that this relevance feedback approach kind of like worked the best? That was sort of like our strongest feature, and this sort of like where this work sort of like built upon. Like here we have this query, we retrieve text, and then we look which entities are mentioned in the text, and we try to get more mileage out of this piece of information. So what we're doing in ENT Rank is that we actually first start retrieving a candidate of paragraphs. Here I'm actually working with paragraphs of Wikipedia, which were released with the TREC CAR corpus, and we also recently released a 2020 Wikipedia corpus. So if you ever wanted to have like an easy to work with Wikipedia that has like all hyperlinks contained, please go to my website, and that's what we're using here. So we have a kind of set of paragraphs, such as, you know, the ones with Volkswagen, and we derive sort of like a preliminary graph of entities where the nodes are entities. And whenever two entities are mentioned in the same paragraph, we give them an edge, we connect them with an edge, and the edge is annotated with this paragraph where they were co-mentioned in. So you can see that the same two entities might have multiple edges with multiple paragraphs whenever they are co-mentioned. That's okay. You may ask, why did I not use relation types? And the problem is that if you just bring, like, relation types sort of like these very brief relation attributes, and often a lot of information gets thrown away with them. And you wanted to be able to fall back on the raw text and to use maybe more information retrieval methods. Mostly because we want to hedge our bets and want to be able to answer queries that even those that didn't really fit the relation extraction schema that we use for extraction. So by having just the paragraph attached to the edge, we sort of like keep our options open. All right. So next we're going to extract different types of features. We have some directly about the entity that we're trying to rank. Like here, this purple one is the one that we try to say how relevant it is. So we have features for this entity, and we have some features that talk about neighborhoodships, like how do you call that? Well, features of neighbors. And we can have like more features about text and about the role of two entities in that text. There might be more entities mentioned in here, but like this is sort of like 3 kinds of features that we wanted to model. And earlier we didn't really have a good way of modeling it. So this is sort of like the framework for how to do it. So at the end, and I'm going to talk more about this is sort of like the abstract. We collapse these graph features for each entity, and then we use machine learning for efficient rank score prediction. Okay. Let me talk about, for 30 seconds, how people were doing it so far. In fielded retrieval, that's like a really old technique. We have sort of like documents that have different fields. For example, you could have one document per entity. Let's hear a document for Lisa, where one field contains the name, the next field contains the descriptions, and then another field sort of connects sort of like other entities that this entity is commonly sort of like connected to. We can have that for Lisa, Tom, and the prince. And you see sort of Lisa as sort of like has a friend, friends with Tom is friends with Lisa, and the prince wants to be friends with both of them, but no one wants to be friends with the prince. I'm not sure why, but I think it's a good question. All right, so and so far most of the entity ranking work fell into a pattern where we take these information, we construct a feature vector for every entity, one for Lisa, one for Tom, for the prince, and then we learn a linear model, like a linear ranking model, where we have this unknown parameter theta, and we take the inner product between theta and that feature vector. More recently, you can also use deep learning, but it's still kind of like the same idea. It's just like instead of a linear model, the model has gotten a little bit more complex. All right, and on the next slide, I'm going to make a big fuss about modeling a graph. I want to just give a quick shout out that like whatever previous work we had, they also had a means of sort of modeling something about a graph, where if you would have Lisa in the field of another entity, and now the query would be something about Lisa, yada, yada. So we have a match here. Sort of like that means if Lisa is relevant, then Tom is also relevant just because we have Lisa in here. So there's sort of like some aspects of a graph that will also be modelable under the previous models. And I just want to like acknowledge that. But the problem is if you model it like that, then all edges are kind of like equally important, and edges there or not. And all you're saying is, how much more is this edge important over a hit in the name field or the description field? Okay. Right. So what we wanted to do instead, we wanted to have more complex features that we wanted to be able to model about entities, neighborhoods, and text. And we want to build a graph with query-specific edge weights. That means like it's not just edge important or not, but we want to be able to have the same graph of 3 entities that have different weightings to different queries. Let's say if you have query 1, then this entity might be super relevant in these 2 relations, but not this one. But then we might have another query where things are completely different, where these 2 entities, that these relations really matter, and this other entity was just in there, but it wasn't really like that important. And we wanted to have a way to teach machine learning how to predict these weights so that we can do something with them. All right. So the quick overview I'm going to like talk about in the next few slides is first we retrieve text and entities for the query, then we build a candidate graph, and then we associate all edges and nodes with features that indicate their relevance for the query, and then we learn feature weights with learning to rank, and we combine this at the end into like a rank score for entities, so we can do entity ranking. Of course, I'm like leaving out a lot of details. More are in my Segaya paper, or can I send me an email? I always like to hear from you. It's so lonely these days. Please send me an email. I'm happy to chat. Okay, So the idea is that first we create a candidate graph by kind of creating, like retrieving some passage ranking. Okay, so we have some text here and some text here. The next step is to run an entity linker on these passages so we know which are the entities mentioned in which of these paragraphs. And now we're going to build a graph around these entities that are mentioned in any of these paragraphs. All entities are going to be nodes, and I'm going to talk a little about edges now. So whenever we have a paragraph and it mentions two entities, like here Lisa and Tom, we're going to add two edges into our graph. One from Lisa to Tom and one from Tom to Lisa. And each of these edges are sort of like associated with the paragraph where they were constructed from. So we have like these pink fuzzy edges come from this one. And in the green one, we have three entities, which means we're going to have 6 directed edges here, right, between every two entities. And also here we keep track of the origins of where all these edges are coming from. In the next step, we're going to derive various kinds of features. And here we have a lot of like modeling power between, are query terms mentioned on the Wikipedia page, NC's Wikipedia page? Do we have, I don't know, a hyperlink between these entities and neighbors, bibliographic coupling, co-coupling, and we can also include other features about the text, such as, you know, the BM25 score of the passage is a simple one, but we can sort of like go more into like semantic role labelings, relation extraction, and so on. Although in this work, we literally only use passage features and entity features, and we use sort of like entity features of neighbors to kind of like transfer it. So we use dumb features in this framework. Right, so we have these features now, and we're going to annotate each of these edges where we know from which paragraph it came to with a feature vector. And I'm only focusing on text features here, and the rest is sort of like a little bit simplified, follows like analogously. So essentially, we just take the feature vector that we derive from a pair of entities in a passage, in a paragraph, and we stick this whole feature vector onto this edge. And there's some normalization, and the paper talks about why this normalization is important. So the next step is we have these multi-graph edges. So we have like multiple edges that point between the same two entities. We're just going to collapse them. In particular, we collapse them in the following way. We're going to have different feature vectors. If we have neighborhood features, we just take that feature vector. If we have text features, we're going to have possible like multiple paragraphs that co-mention the same pair of entities. We have multiple of those. So we're just going to sum over all these feature vectors and stack it on top of our neighborhood features. That's going to be our edge feature vector. And you might ask, why do we have a sum here? Why not any other operation? And the answer is again in the paper. So now what we have here is a feature vector associated with the node and another feature vector associated with each of these edges. And again, they're sort of like directed pointy graphs. Okay, so you can already see entity features, neighborhood features, text features. This is where ENT comes from. All right. So how are we getting an entity ranking out of it? So we're just using a pretty straightforward inner product. And we assume that we first have a score for the entity's importance, and then we have a score for each edge. And you can sort of like use degree centrality to kind of combine all these different scores, right? It would be like we're summing all the edge weights over incoming edges plus the weight, the node weight, and that would give us like a score for the entity. So that would, however, require that we would actually make up a score and put it on the edge. But we didn't want to do that. We want to use machine learning to learn how to create a score that would help us solve our problem best, right? And we can do this by just taking a linear model for node features and one for edge features, and realize that this here is just another inner product, right? Here we have an inner product plus the sum over another inner product. We want to learn the psi and theta. These are like our global parameters, the same for all entities and for all edges. But we want to set these because we want to know which features actually matter. And you can just look at this, realize it's just another inner product that just looks like this. There we stack these two vectors we want to learn into one vector, and we combine our node and our edge features by stacking them on top of one another, and it's exactly the same thing. Okay. And because our edge features with just like neighbor and text features stacked on top of one another, we can just put it in here. And we have a really nice form where we have one complex feature vectors that includes both entities and neighbors and text features. And we have like one parameter that we just want to learn. And this sets off like the form that where any favorite learning to rank algorithm can probably give you a good parameter that you can learn with. I like use coordinate descent with mini batch learning just because it's like super resilient and I can use my favorite optimization metric for it. But pretty much like any other, it just shows like how generic this kind of idea is. And we can do also like use it with like more complicated machine learning models just like for education. All right. There's also obviously a connection to random walk with restarts. Like here we have a node restart probability, and here we have an edge transition probability, which we kind of like automatically learn to do the best job we can for entity ranking. Okay, but you can see that the framework is a little bit more general than just entity ranking and just passages. All right, I'm going to quickly wrap up. So here's just some suggestions that it actually works. Initially, I kind of like opened with the Zika fever example. And this is sort of like the graph that we kind of like learned. These are all the entities, and here are the edge weights that we learned with our machine learning method for that query. And I was actually surprisingly thrilled, I was really thrilled to see South America here, because I realized that South America, despite the fact that there was like a major Zika outbreak in like 2015, it doesn't mention Zika fever on the Wikipedia page. The Zika fever page mentions that, but it was held out of our corpus because it was a query, and TREC CAR pages of queries are being ditched. So it was actually great to see that it was able to identify that that South America is an important entity for the Zika fever query, just from like third-party references that people talk about it, and realize that this is sort of like important. All right, I can show you like more numbers. Mostly I say it actually works, despite the fact that we were only using dumb features in this framework. It works both on TREC CAR, which is like about generating documents, but also on like other more question answering centric entity ranking benchmarks like Wikipedia entity. All right. So the main thing here is that I want you to remember from this work is we have a means of sort of like giving us like more options with what you want to model as features or how you want to think about the data. And we can sort of like construct this sort of like multi-graph, and we find a way to sort of like collapse things to at the end learn a query specific graph rate where all the edges just have like numbers attached to them, and these numbers just get predicted with our machine learning model. We can sort of like use this, for example, with degree centrality, then also like rank entities. But the thing that we were really after was like the graph. And there's still like many questions that you probably have that I also have that I didn't have time yet to really look into. If you're interested in like data and code, it's all available on my webpage, and I'm happy to kind of like hear back from you. I don't know how many minutes do I have? I would otherwise maybe like spend another 2 minutes to talk a little bit about what we're currently working on.
Yeah, actually, you can spend plenty of time. We have a half hour left.
Okay, perfect. Okay,
so yeah.
Great. So we also have like more time to discuss more. That's
yeah,
great.
We do. Yeah.
So I want to kind of just quickly say a few things about what we're currently working on. So if you have any thoughts or any like, hey, I'm working on the same things, then please do let me know. I'm happy to always like work with people, especially in these lonely times. This is kind of like a screenshot of my lab. You can see I was like overly excited and not particularly pretty in this picture. There's like one piece of ongoing work to actually include relation extraction into ENT Rank. As I said before, ENT Rank in the work that we published at SIGAIA was kind of only using dumb features about entity rankings and paragraph rankings and not much else, but the framework is like gives you a lot of options, and we kind of like, and one of the things why we were doing it, because we wanted to learn something about, how can we include these relation extractions, and in particular relation extractions versus co-occurrence mentions versus other kind of ideas that we might develop to say how two entities are related and whether their relevance is actually important versus not. and ENT Rank is sort of like general enough that we can sort of include all of that ideas, and Pooja and Stavan are kind of like working on that. And I hope you guys will see them at a conference sooner or later. Shubham over here, he actually works on sort of like the inverse of it. He works on how can we, if you have a query on an entity, how can we identify passages that sort of like tell us how this entity is actually relevant for this query? So it's kind of like an explainability kind of thing. But the reason why I'm interested in explainability is because, well, we have the queries, we have relevant entities. How do we find the past passages? And the hope is that this is going to help us on that mission. Matt up here, and also like Jordan and to some extent Shubham, are working on what I call entity aspect linking. So the idea is you might have entity links. They say here's text, this is the entity that's mentioned here, but then often that's like doesn't give you a lot of information, especially if you have a very generic entity like United States. There are many different facets of the United States, and just having that entity link, you don't know whether United States is mentioned as of like foreign politics, finance, Silicon Valley and tech development, academia, and so on. So we often actually want to know a little bit more than what a strict entity link is giving us. And entity aspect linking is our way to kind of get a more fine-grained view on what this entity means in that particular context. Also, that hopefully it helps us write better articles, or just like be generally like useful. And I call that sort of like which aspect of an entity is mentioned in a particular passage. We also recently put out like a large data set along with the publication at CRKM about kind of if that's sort of like a task that you think you would like to work on. The data is up there, use it, and if you have better results, let me know and I add your number to our website. Samantha, who's unfortunately missing from this picture because he was doing an internship during the time, is working on subtopic extraction for passages and entities. Also with the ideas like once we have relevant entities and passages, before we just put them on the article, we may kind of maybe like sort them a little bit so that you have sort of more coherent, topically coherent areas of this article. That's kind of like, I think, really interesting. And some of you may know that I originally did a PhD on topic models. So that's still something I think is kind of like, would be great if you could solve it. And I don't think topic models are the right way of doing it. But maybe we have like some new ideas to do that, also like with the help of Word and like better end-to-end models. And finally, David here was actually looking at how can we, if you would generate an article, if we were to generate an article, how can we actually tell whether the information on that article is actually useful or not? And so far, people use Rouge, and everybody finds Rouge really unsatisfying. And I was like, I find Rouge so unsatisfying that I was refusing to like work on that part unless we have better evaluation metric. We do have something better. It's currently under submission, so I can't really talk about it. But I hope the paper gets in, and I hope that this is sort of like a good way forward for actually evaluating like articles that kind of like are generated for a particular purpose. All right, this is my last slide, so you can already like think about some good questions. So what I'm trying to do in like a bigger vision is to recycle the web, and so that we can generate relevant articles for queries that don't already have sort of like the perfect information on them, such as, you know, answering questions about why ice skates work or how sand flows. Or where the static charge comes from when you rub your hair with a balloon or other silly things. And the idea here is that we want to work on two directions. We want to, at the same time, generate an article that's like great for human consumption, because humans just like to read. They need to start on one end and end at another. Everything else is like really confusing for humans, at least for me, humans like me. The other thing that we want to do is like on the side, generate a small knowledge graph that will be actually machine readable. And you can imagine that, you know, once you have generated this article and present it to a human, the story doesn't end there. Probably the human will have like more follow-up questions on the information that we just presented. So you want to keep the knowledge graph around and maybe then kind of like put more information in context with information that you already presented first. Number one, you already have an idea of what the user maybe already know. Number two, you might be more consistent with the next answer with respect to the first answer that you already gave. Otherwise, the human might actually wonder whether you actually passed the Turing test or not. Anyway, so this is all like the two directions, and I think there's a lot of work to do. And I hope you have some great questions or insights or comments, and I'm interested in all of them. Thank you.
Okay, thank you. I'll clap for everybody. since you can't hear everybody.